Hello everyone, here is a question based on hydrogen emission spectra. The ratio of wavelengths of the last line of Balmer series and the last line of Lyman series is how much? Last line means the N2 value is gonna be infinity in both the cases. We know that the energy for a stationary state N in the case of hydrogen emission spectra is equal to minus Rydberg constant times z square divided by n square. Z is the atomic number, n is the value of the stationary state. The energy difference in that case, delta E, will be equal to En2 minus En1. Now here, in the case of Balmer series, the N2 value is gonna be infinity and the N1 value is going to be 2. For Lyman series, the N2 value is once again infinity and the N1 value is going to be 1. And this one we can write it as RH. I am not putting negative sign here and therefore I am directly writing it as 1 by N1 square minus 1 by N2 square. Here they are asking the ratio of wavelengths. We know that energy is inversely proportional to wavelength. And therefore, let us write it this way. 1 by lambda b is equal to the Rydberg constant times the n1 value is 2. And therefore, 1 by 2 square minus 1 by the n2 value is infinity. So, 1 by infinity square. 1 by infinity is we can take it as 0 because infinity is a very large number. So something 1 divided by something very large number, it's gonna be a very small number and therefore we can take it as 0. Therefore 1 by lambda b is equal to Rydberg constant divided by 4 and therefore lambda b will be 4 by Rydberg constant. So 1 by lambda L for the Lyman series, this will be equal to simply Rydberg constant times 1 by 1 square will be 1 and 1 by infinity square we can ignore. And therefore 1 by lambda L will be simply RH and therefore lambda L will be 1 by RH. Now they are asking the ratio lambda b divided by lambda L. Therefore, this will be equal to 4 by Rydberg constant times Rydberg constant divided by 1. This will cancel out and therefore this is simply equal to 4. Therefore, option 4 is correct.